Good evening, everybody. This is Adi Pai from the Multi-Class 2024, and I'm here to give you a quick lesson on iterated integrals and start off some double integral stuff. Just we'll see how far we get. But yeah, this is chapter 14.1 in the Ron Larson textbook, and it's going to be a quick overview on some of the problems, some of the notes, just a quick example of how things work in iterated integrals and how they can be used to solve some problems. So yeah, the integral is something we're all pretty familiar with. We've seen it in BC, we've seen it in multi, we've seen it in pretty much every course you've taken since junior year, if you're in multi right now. And it looks like this. We've all seen the typical, like, x dx, and that would equal what? X squared over 2 plus c. We've all seen this, but let's say we had something a bit different. Let's say we had a partial, right? We had the function f, and the partial of f of x, y, with respect to x was equal to, let's say it was 2xy, using the notes, the textbook's example. So using this, we're going to go into the integral process again, but we're going to do it a bit differently because we have two variables here. So if we want to solve for the original f of x function, we can do it like this. We're going to do f of x, y equals to the integral of 2xy, and because this was the x partial from back here, we're going to do dx. Right? That makes sense. So at 2xy, integral 2xy dx, and if we solve that out, obviously we're going to get the constant y is going to be taken out, so we're going to do equals to y integral 2x dx, and now it's just a very basic integral that we've all seen before. That's going to equal y, x squared. But here's the thing, right? We also have a plus c, but the c isn't just c anymore because we have this entire y variable here that could have its own function to it. Because if we look back here, let's say the function was originally x squared y plus 6y, maybe. We'll just call it that. Why not? The x partial of this would equal to, or well, let's compare two things. The x partial of that would equal to, what is it? x 2xy plus 0. But if we had this other function, x squared y plus 7 maybe, that's still 2xy plus 0. So this other term, this plus c, might not just be a 7, it might not be a constant, it might be a y function as well. So we change things a little bit here, and we actually go here and we do c of y, just to confirm that, this could be, just to make clear that this thing could be a y function instead of just a constant. It might be a constant, it might not be, we don't actually know. Okay, so cy is a function of y, and you can only, the true lesson behind all of this is that you can only get part of a function back if you're integrating a partial. You can't get the entire thing, because there's other function, the other variable that might come up from somewhere that you kind of lost in the process. So that's why we don't really always integrate partials in this way, because you can't always figure out what this actual thing is. So we're gonna try and I think later on in the course this is something we might do. I'm not really sure yet at this point in April of 2024, but I know it's a possible thing you can do in some areas of multi. But we're gonna just ignore that, and we're just gonna go on and carry on to see what these things actually could be. So if you integrate with respect to y by holding x fixed, you can still create this sort of replica of what the function could look like, but it's not super useful in figuring out how things really work. So we're going to try and do things a bit differently to figure out how those things can actually be done. So the way we can figure out what y and x both can equal is by taking not one but two integrals. So let's say we're going to do this by taking the integral of an integral of some function. I don't know. We're going to call it, the textbook uses this example, but I'm not really a big fan of that one. Let's try out, yeah, fine. We'll do example 2 on page 985. Okay, so let's say we have some function, and that function is equal to 2x squared over y squared plus 2y. Let's just say that's our function. We're going to call that f of x, y. All right, so let's say we want to find out the integral of this thing from a certain example. So let's say we have a, let's do a thing. Let's say we want to find out this iterated integral. So iterated integrals are essentially integrals that go from over one bound and then a second bound. So we saw over here that this thing is kind of a problem because we lose one entire variable, the function. So, but what if you did this? What if you had an integral from a to b, and then a second integral from c, that's not a c, a second integral from c to d of some function f of xy, first with respect to x, but then with respect to y. So what you could do here is you could evaluate this inner integral first, take that, this inner integral first, take that result, plug into the second integral, and get one with respect to y, and get one final function that was integrated over both different variables. That'd be pretty cool, wouldn't it? So it turns out you can do that. That's what you actually do for these functions. So let's try it out. We have our function here, and let's say we want to integrate over a region. So let's make a quick graph here. And let's say we do some colors, why not? We have a line, and this line, this is the first quadrant, right? So this is a very basic function we've seen before, and this is a slope of 1. We're just gonna call this line y equals to x. We've all seen this line before in like literally 6th grade, I'm pretty sure. So it's pretty basic. We've all seen this before. And let's say you want to integrate over a certain region. You could, if you're taking integral, let's say from here to here, normally you would shade in this entire thing. You'd find the area of that, and you could do that with one integral. But let's say instead you wanted not that area, but instead just this area, just that little sliver over there. How could you do that? That's a bit different, right? That's not as elementary as just getting the area under the curve. Now you could obviously do some area like here minus some other area here, but like, you know, we're not gonna do that. We're gonna do it a different way. So this function is rather basic, and you could literally just do 1/2 base times height and figure out, the area that way. But let's just say, for the sake of the argument, that we're gonna try and do a fancy integral to make things a bit more interesting. So we're gonna label these points real quick just to make sure we're clear on where this is. This is 1, this is 2, this is 1, this is 2. So we want to find the area inside this triangle, which starts off at this point, which is 1, 1, and ends at this point, which is 2, 2, and this last point is going to be at 2, 1. So how do we find the area of that triangle? Well, we're gonna actually do an iterated integral. And the way it's gonna look is something like this. So we have our function, we're gonna write down our here, let me make some more space between those two things. We know for a fact there's gonna be two integrals, one to find the area between the curve and one to like spread across the region. And then we're gonna have our function, which is going to be 2x squared over y squared plus 2y. All right, so how do we actually go about setting this up? Well, let's take a look. So we're going to look at the function here. So let's take a look at the bounds that are making this thing kind of work. So if we look at the y bounds, this is actually one of the bounds here, and the other bound is this over here. Or sorry, I missed. One sec. So one of our bounds is that line, right? That line is actually its own bound. So that line y equals x is actually a bound. And the other bound is going to be when y is equal to 1. That's this other bound over here. So if we want to find, like, these are all kind of bounds that are making this function stay in place. We have, that's a bit off, but we're gonna one's over there now. So we have these these 4 bounds that are kind of trapping this function in one place, that are making it very clear where our area is. And to restrict the area in that way is how we need to calculate area. So the first thing we're going to do is we're going to do some like 2 fell swoops. The first swoop is going to be over y, and the second is going to be over x. So let's look at y. Okay, so the things that are concerned with y is, let's make y blue. Why not? This is a line that's dealing with y. This is setting the y bound up here and down here and up here. And this thing is also setting y. It's making sure y does not go below that line, whereas these two are dealing with x. So we can see in this area of the triangle, this triangle area here, the upper function is always, the upper bound is always this diagonal line, right? And because the upper bound is this line, we're going to set that as the upper bound in our actual integral. So this upper bound is always what? Y equals to x. So x is actually going to be the upper bound for the function, because we're trying to figure out the bounds of y, right? So the upper bound of y is literally just x. So let's say we're going to integrate over y first. We're going to go and put dy right here. So we're going to go ahead and just put that down. And then we're going to get our bounds. So we know for a fact the upper bound is going to be y equals x, because we see that this line is literally the upper bound of our area that we're trying to solve for. So we go ahead and put an x over there. Now what about the lower bound? If we look here again, this other blue line we drew is at a straight horizontal line, and that is at y equals to 1. So it's as easy as that. We just see that the lower bound, that the function is always, the area is always above, is going to be 1. So we have x at the top, and we have 1 at the bottom, as you can see there. All right, so now we've essentially integrated over y. We've gotten the y bounds ready, but the second thing we need to do is do the same thing to x. Now, for x, it's a bit simpler. So in y, we actually had a function bound here, as you can see, with this diagonal line. But in x, we have two very vertical lines that essentially establish what x is going to be. Let's go to green for x. Why not? So we have the first line here and the second line over here. And we're going to integrate from small to big. So we go from 1 to 2 to get our two equations. We have x equals to 1 and then x equals to 2. So we can just write that here as you would expect, 1, 2. And just to make things very clear, because it's going to help us out later on, we're going to write down a compound inequality to, that's a term, right? Compound? To express our bounds. So let's start off with y. I'm going to put it in red again. So the lower bound of y is 1. So y is always less than or equal to 1, greater than or equal to 1, and less than or equal to this upper function, which is going to be x. And then the second one is going to be the x bounds, and that's just going to be 1 is less than or equal to x is less than or equal to 2, because we can see here it goes from 1 to 2. That's not too bad. So we have our two bounds here, and we have our integral set up as follows. So now we're just going to, oh, whoops, forgot a dx there. That's not a marker, dx. Okay, so now we have our iterated integral set up completely ready to go. Now, let's actually go about solving this thing. Let me just put that there for posterity. All right, so let's go about solving this thing. So first thing we're going to do is just isolate this middle integral here. We're going to grab this and pull it out. So that looks like this. 1 to x of 2x squared over y squared plus 2y with respect to y. So because with respect to y, this x squared is literally just a constant. We ignore that. We completely pretend it doesn't exist. And now, if we integrate that, we're going to do it as follows. So here is our very basic integral that we can solve with these bounds. Okay, so we've isolated this one inner part, and now we're just going to solve it with respect to y. Now, the way you solve this is very much like a normal integral. You just kind of ignore the fact that x squared is a variable. You just pretend it's a constant, and you pull that out, and you literally just integrate 1 over y squared and then 2y. So let's break it up even more to make it a bit simpler. So we integrate 2x squared over y squared from 1 to x, and we integrate 2y. It's dy, this is dy, from 1 to x. All right, so 2x squared over y squared is, it looks a bit troublesome. It's not that bad. So 2x squared is just our constant, so we pull that out, so we can do 2x squared, and now it's just the integral of 1 over x, 1 to x of 1 over y squared. And then the same thing we can do here. We go from 1 to x, pull out the 2 of y dy. All right, and we do a plus sign in the middle. Cool. The integral of 1 over y squared. Now, this is some good practice for us. The integral of y to the negative 2 is just going to be negative 1, or negative y to the negative 1. Right? Yeah, negative 1 to the negative 1. So 2x squared times negative y to the negative 1 from 1 to x plus 2 times y squared over 2 from 1 to x. Now, let's plug these in. Plugging in x for that one, we get x to negative 1, negative x to negative 1 times 2x squared. That's just going to be negative 2x. And, right, yeah, okay, minus 1. Why did it 1 to the negative 1 is just 1. Negative 1 is positive 1. That's plus 2x squared. All right, next side. Plus, first we're going to plug in x. So x is going to go on the top bound. That's just going to be plus x squared. And then minus 2 times 1/2 is just 1. So yeah, it just ends up being that. Let's evaluate that. We have 3x squared minus 2x minus, wait, minus or plus? Yeah, minus 2x. Minus 1 is the answer to that integral. All right, so now we're halfway there. We did one integral, and now we're going to plug that answer into our second integral. So when you plug in these bounds, it's a bit tricky sometimes to plug in like a functional bound, but this one isn't too bad. It's just literally x, so we can get away with just plugging things in and making things work out nicely. Sometimes your bound list looks like 4 minus x squared or something. That's a bit more annoying, but it's the same general process. You just plug in you plug that entire thing for your y value, and you just kind of solve from there. So if you do it correctly, you should end up with a new function that is now integratable. I don't know what the word is. And now we're going to plug that into our second integral, which was as follows. The bounds were from 1 to 2. 1 to 2 and 3x squared minus 2x minus 1. And now we're going to go to the dx. Look at that. We had two integrals, now we just have one. And this is a very basic integrable function. We're just going to make it go to x to the third minus x squared minus x. And that's from 1 to 2. Did I hear that right? Yeah, I did. Okay, cool. Now, plugging these in. First thing is going to be 8 minus 4 minus 2 minus 1 minus 1 minus 1. Yeah, sweet. So that's just going to be 2 is that first product, or the first sum, and minus -1, so 2 plus 1, and that's just going to equal to 3. Awesome. So this seeming mess at the top ends up just being 3. So as you guys see, it's really not that bad to do a lot of these iterated integrals. It just looks really tough at the start because it's just that ugly mess of, two integrals, and you have that whole, painful thing. But it really works out quite nicely. Like in the end, it looks pretty good, and you just get a nice number at the final answer. So the same process works for other integrals where the function is less pretty than, y equals x. So let's say, let's do one more, and I'm gonna kind of rush this through a little bit because this video is gonna be pretty long otherwise. I'm just gonna make it a bit different. We're going to use the second example from the book where it's an area of a plane region. And we're going to use the just a general equation for this. So we're going to say you have the following graphs. This is going to be y, x, and let's say a good old function that we all know and love, the sine function. So y equals sine of x looks something like that. And we're gonna mark these out. That's 0, obviously. We're gonna have this one be, what is that, pi over 2? Yeah, pi over 2. Pi over 2. This is pi, 2 pi, 3 pi over 2. Lovely. And I'm sure you guys all have great memories of this function, and we're going to do it again to make sure that we still remember it and haven't forgotten what it does. So then we're going to do a cosine function, just to make things even more interesting, and that's going to look like this. Awesome. And let's say we want to find the area of this yellow shaded region. Why? Because we feel like it. That's why. And this is, at first glance, kind of ugly. So the way you actually do this with double integral, like I know you can do it with single integrals as well. Like we probably did it last year as well in BC, where you did something similar to this and solved it with, normal integrals. But we are different here in multi, and we do things more fun. So we're going to do an iterated integral for this as well. Let's call this region R, just for the sake of good practice, because we're going to call a lot of things R in the future as we get into more complicated integrals. So it's a very similar process. So here, let me just label these functions real quick for you, just to make sure we don't forget. Sine x and y equals to cosine x. Now, looking at this, we see very clearly the sine is the upper function and the cosine is the lower function, right? So we're going to just do the exact same thing as before. Over here, we had y equals x, the top function, and y equals 1 is a lower function. Here, we're going to trace out that exact same curve. So the upper bound is going to be along this function, and the lower y bound is along that function. And we get that little toothpaste-like squiggle-shaped region as our final thing. So we're going to set up our iterated integral. We know for a fact it's going to be 2 integrals, and it's going to be over a function like some area function, and then d blank, d blank. Okay. So now, the way we decide which variable goes first, like this could be y or x here, it could be y, it could be x, it could be either one, and the way we decide which goes first is by kind of looking at a, like, so if we look at this, right, so we want to pick a order where the functional bounds are nice to solve, right? So our options are this: if we do y as a function of x, like we're given the function in two forms, right? Y equals sine of x and y equals cosine of x. So if we integrate over y first, we can just use sine and cosine as bounds. If you integrate over x first, you gotta use inverse sine and inverse cosine as bounds. And personally, I don't know about you, but I would much rather integrate sine and cosine than inverse sine and inverse cosine. So we're gonna do y bounds first. So we're gonna do dy dx, because then we can just make it a bit simpler. So the area function is actually just literally nothing. You don't plug in anything to this, because all you can do is kind of compensate it by adding it to the bounds. And we're going to do a functional bound for both top and bottom. So we marked out in green here the parameter of the, like the bounds of the actual area. So if we look at it right now, we're going to see that this goes from sine x at the top and cosine x at the bottom. So we're literally going to grab those exact same bounds. We're just going to plug in sine x at the top and cosine x at the bottom of these bounds. And now we're going to look at the x bounds. So this, we draw like a little like a line here and a line here. I drew it kind of badly, but that falls in the middle of the interval from 0 to pi over 2, and that falls in the middle of the interval from pi to 3 pi halves. So we know for a fact, because it's in the exact middle, this is pi over 4, and this is going to be 5 pi over 4. So now we know that the x bound is from pi over 4 to 5 pi over 4, and we're going to just copy that down as follows: 5 pi over 4 and pi over 4. And let's erase these. Awesome, and that is literally our integral. You may be wondering, where's the thing in the middle? Why is there no function? Well, so with the double integral, so with the ones like this, where you could literally solve it with a single integral if you really wanted to, it's kind of baked into the limits, into the bounds. So by adding functional bounds, we essentially compensate for the fact that we're not subtracting one thing from another, and we can just do the function as just like, the inner function is just like literally 1. So while there is nothing there, there is a 1 there. The one is actually there, but it looks like there's nothing because there's no, nothing written in the middle. But because sine and cosine are the bounds, because these are our bounds, it works out fine, and it's totally valid to do nothing in the actual function that you're integrating, and it just kind of works out as a, as an integral. So yeah, it's just integrating over the area between those two curves, and that works out fine because you're using functional bounds. Cool. So now you integrate this, and you do it as follows. So the integral of, let's grab the inner one first. So we're going to just separate it into sin x over cos x dy. And the integral of 1 is just literally y. So you now have y from, that's not cosine, whoops. Sine x to cosine x. In other words, sine x minus cosine x is that function. And now, the second integral, you're going to grab this, and you're going to plug it into this. You have pi over 4, 5 pi over 4. And you're going to evaluate sine x minus cosine x. Now, notice something interesting about this here. If you separate this out, you actually get the integral, which is 5 pi over 4, pi over 4, sine x, minus pi over 4, pi over 4, cosine x. And these are both dx, of course. And that's really interesting, because if you remember from BC last year, if you were told to find that area R in BC, you would have done it like this. You would have found the area under the sine graph, which is just, what is it? It's like, if you just did the area under sine, let's make it in blue, it would be all of this, right? And then you find the area under the cosine graph, which is going to be all of this. And that, whoops, I went too far. And that is going to be the exact same output as this double integral we're doing here. So that's really interesting. That's how you can convert a single to a double integral, and how you can do the same problem in different ways using iterated integrals and just your standard everyday integral from last year. So personally, I think our method's cooler. But the reason that there's no function bound in here is because of that, because you're just doing the same thing and you're just subtracting this thing from the other thing, and you end up with that integral. So if we evaluate this, you guys know how to integrate sine. I'm just going to skip past that a little bit. You end up getting an answer of 2 rad 2. And that kind of just works out by integrating sine and cosine as you usually would, like there's nothing different there. And you guys know how to do that from last year and probably more practice this year, so I'm just going to leave that part out. So what have we learned today? Iterated integrals are very similar to regular integrals. It's just an integral that you're doing twice, and the bounds are functions usually. That's the only difference to make things a bit more capable. So the reason you integrate twice is first to get you do over y and then you do over x to get your bounds over a certain region and then over a certain other region, and that works out the same way. To wrap things up, let's just write the bounds of this integral in a compound inequality as well. Good practice. So we're going to have sine x is the upper bound for y, and y is going to be greater than cosine x. So y is always going to be above the cosine and always below the sine. Next, time for x. We're going to start off with pi over 4 less than or equal to x less than or equal to 5 pi over 4. And that's going to be, in total, your region R, which is going to be that yellow shaded region over here, as you can see. Cool. So that is going to be how you do iterated integrals and how you kind of see we're going towards double integral territory, but we're going to start that off in the next video. Thank you guys. Have a nice night.